All right, everybody. Thank you for joining us today. We have electronic circuit protection talk with a partner of ours, Emphatec. I will hand it off to them. First, want to introduce them. We have Don Robinson. He is the president of Emphatec. They're based out of Ontario, Canada, as well as Vinesh Kumar. And he is the sales manager for North America, also based out of Canada. Just a little background on them. They formed in 2003. They broke off as an engineering production department of Weidmuller. They offer lots of industrial automation products and specialize in custom products for a lot of specific applications. And we're going to go over some of those today. So Don, if you want to take over.
All right. So, oops. So this will stop sharing screen. Do you want to continue? This will stop others. Okay, so did the presentation pop up on everyone's screen?
Yeah, you're good, Don.
Okay, so today we're going to talk about electronic circuit protection. Okay, that didn't work. What is it, for starters? Compare it to fuses and circuit breakers, talk a little bit about some applications for it, and some of the regulatory issues. This is the CSA and UL requirement issues, and that's a bit of a confusing situation right now. So start with just some basics on overcurrent protection. You have a power source that's able to deliver a short circuit current of some amount. You have your overcurrent protection device, whether it's ECP or a fuse or a breaker. It should have an interrupting rating. If all goes well, it can interrupt more than the power source can deliver into a short. And then you have two situations. There could be a short circuit in the wiring, or there could be an overload in the final device, the load. Short circuit protection being more branch related and overload protection being more supplemental, but we'll get into some of the details. So question you always have to ask when you're thinking about overcurrent protection is, what are you trying to protect? You're either protecting the wiring from catching fire in the event of a short, which is more branch related, or you're doing overload protection. For example, a motor starts to draw more current than it should be, so the breakers trip and shut the motor off. Short circuit protection requires a protective device to be able to withstand the short circuit current. So if you're familiar with branch protection devices, they may have a 10,000 amp interrupting rating. So as long as your source can't deliver more than 10,000 amps, you're properly protected. Overload protection is not exposed to a short circuit current, so it doesn't need the same level of interrupting rating. The electronic circuit protection product. It's an electronic circuit, doesn't have mechanical parts or fusible elements. Includes a current sensor and then some sort of a solid state switch, whether it's a transistor, a triac, or a MOSFET. So when the current exceeds a set point, you open the switch, interrupting the current. So it sounds a lot like a circuit breaker. And when some companies first started promoting their ECP product, or what became ECP, several years ago, some companies launched them as electronic circuit breakers. Didn't go over real well with the approvals people. The definition of circuit breaker in North America, either the National Electrical Code or the Canadian Electrical Code, very specific. Device designed to open and close a circuit by non-automatic means, which means manually turning it on and off, and to open automatically on a predetermined overcurrent without damage to itself, which would seem to be logical, but supplemental devices can actually be damaged. So this this implies that you have to be able to manually turn it on and off, which an ECP product, you could design it to do that. And it has a trip point and a trip curve. So it sounds like, yeah, okay, these things are circuit breakers. But that when you delve into the definition of breakers, you find that a circuit breaker in North America has at least a 5,000 amp interrupting rating, typically 10,000 amp, works to standardized trip curves, B, C, and D, you know, whether you want fast trip or slow. Historically not rated less than 15 amps, but that's changing. So a electronic circuit protector does not meet these requirements. You're not going to get a 10,000 amp interrupting solid state device easily anyway. So they don't meet the definitions in North America for circuit breaker. So that's why everyone had to come up with a new name for them. And the name that's settled is ECP, or electronic circuit protector. So the next question would be, is an ECP actually the equivalent of a supplemental device? Supplemental devices look like breakers, but they have lower interrupting ratings. So that kind of matches with the ECP. The interesting thing is, according to the standards in North America, a supplemental protector only has to work once. It doesn't necessarily have to survive the fault. It has to interrupt the current, but it could be completely toast after that. So don't think anybody wants to put in an electronic circuit protector only to have it work once. So yeah, maybe it's supplemental, maybe it isn't, and we'll get back to that in a few slides. So if we look at a DC application where we have a DC power supply, we could have three options on the output between the power supply and the loads: the electronic overcurrent protector, the circuit breaker, whether branch or supplemental, and a fuse, which could also be branch or supplemental. If the ECP cannot withstand the short circuit rating, it's not suitable for the application. Makes sense. They do not have 5,000 amp interrupting rating, so they can't be classified as a breaker. We said that. And in the event of when you're using it with an AC/DC power supply, the available short circuit current is much less than 5,000 amps, so you don't need a branch rated device. It would be overkill to use branch fusing or branch breakers on the output of a DC power supply. The electronic circuit protector in this application, they're very fast. And they have very accurate trip points if you want to program them that way. So you could have an electronic circuit protector set to trip at or pass 30 milliamps continuously and trip at 32 if you want. You're not going to get that level of accuracy from a breaker or a fuse. You might have a manual on-off on an ECP product, but what you won't find on many electronic circuit protection products is an interrupting current rating. They give you the trip point rating. They can tell you, well, you'll trip within this range, or you'll trip within so many seconds or milliseconds. But I haven't seen one yet that says, yeah, you can interrupt 200 or 500 amps with these things. So the branch breaker, it's got different trip curves, high interrupting rating, overkill for use in power supplies. The short circuit protection of within the power supply itself is probably going to be faster than the branch breaker. So it would beg the question, why bother putting in a branch breaker? You could put in a supplemental, which again is technically not called a circuit breaker. Different curves available. Trip point tolerance is much broader than the ECP. Response time should be faster than the circuit within the power supply, which it may or may not be. Interrupting current ratings anywhere from 200 to 500 amps are common, could be as low as 30. If you put in a fuse on the output, again, you get the different trip curves. The response time has to be faster than the power supply's protection circuit. Interrupting ratings, not a problem. You can get 500 amps quite easily. Not resettable, obvious. Trip point tolerance, much broader than the ECP, but they're cheap. So the end result is all four appear to be suitable. And by 4, I mean the ECP, branch breaker, supplemental breaker, or fuse. As long as you know what the short circuit current rating of the power supply is. So into a dead short, how much current can your power supply deliver? And the vast majority of power supply manufacturers don't publish that information. So you're kind of left in the dark. And what you really should be doing is on your 24-volt power supply, you put your protective device on the output and you short it to ground. If the device turns off the current before the power supply switches off, you're good. If the power supply shuts off first, your overcurrent protection is not doing much of anything. Some power supply manufacturers have gotten into this, they publish a boost number where they can give this big surge of current for a certain period of time to ensure that the breaker or the fuse blows. That's not necessary with ECP because they're so fast and they have such an accurate trip point that they don't need the big current boost from the power supply. So if you're only providing overload protection, then your protective device only needs to handle the continuous current rating. It's not going to see a short circuit current. The features of the ECP products that make them attractive for overcurrent protection, you can do remote on off. You can send them a signal. The PLC could send a signal turning off the circuit. You can get lots of status outputs. You can get not only just LEDs on there, but you could get digital output to tell the PLC the device is just tripped. Multi-channel is attractive. You could get a single input, 4 or 8 protected outputs, and this lowers the per channel price considerably. You can also get user configurable trip points and time delays. Some of them are dip switches and pots to set up different tripping characteristics. These days, using MOSFETs, you can get a what's called RDS on. The on resistance of the device can be very low, so it minimizes the power dissipation. So if you were using a transistor on the output, it would give off significantly more heat than a MOSFET. So the ECP product is attractive from that perspective, and that doesn't dissipate a ton of heat inside your cabinet. They can have very low trip points, and this is interesting. If you wanted to protect a 20 milliamp loop, fusing, well, circuit breakers are out. A fuse, yeah, you might be able to get a 20 milliamp fuse, but it may not blow until 30 or 40 milliamps. Where an ECP product, you could set it up to say, okay, deliver 20 milliamps into the loop, but trip at 25 or trip at 30. And the idea being that if there's a short circuit in that one loop, the ECP product is very fast, isolate that loop, and there's no chance of the power supply shutting off. So the rest of your system remains operational. The one circuit that had the short goes dead, and your ECP product could give you an alarm output, so the operators can tell exactly what loop is in short circuit. And another interesting feature of ECP is that the MOSFETs, or whatever solid state device is being used to switch the current, they're non-arcing and sparking. So ECP could be good candidates for certification for use in hazardous locations. And as mentioned, the very fast switching time of the ECP can eliminate the need for the boost feature in the power supply. And this is ideal, especially at the lower current ratings. And the whole idea is the ECP is faster than the internal overcurrent protection within the power supply. So power supplies are, in order to get CSA and UL, they have to have overcurrent protection on the output. It can be very fast. But depending on the current levels, it could be very fast, but it's a 20 amp power supply, so it can deliver 25 amps for quite a while. You don't want to be putting 25 amps through 22 gauge wire running a current loop, for example. So the ECP can can protect that loop before the power supply turns off. Disadvantages of electronic circuit protection. These days seems to be just about everyone's offering DC only, where breakers and fuses could be AC and DC rated. They can be expensive, but if you go with the multi-channel units, they can be competitively priced. So if somebody wanted to make a single channel ECP product, could be expensive compared to fuses and breakers, but it might also be Haslock rated where the breaker isn't. So the cost could be justifiable. I've seen some that are using microprocessors internally so that you can vary the trip characteristics. But putting a micro in there could make them more vulnerable to transients and brownouts that wouldn't have much impact on fuses and breakers. Regulatory issues. This is where it gets very confusing for manufacturers. Standards being used to get these things certified. In the US, there's a standard called UL 2367 called solid state overcurrent protectors, UL 508. I'm sure you're familiar with that. UL 1604 was the class 1 div 2 standards. I think that one is being replaced by UL 121-201, the non-incentive products for hazardous locations. And then in Canada, there's CSA 14, which is similar to 508, 142, which is being phased out, and 213 for class 1 div 2. CSA 213 and UL 121-201 are harmonized standards. There's no difference between the Canadian and American requirements. UL 2367 is doesn't have an equivalent in Canada. And if you have a look at the ECP product data sheets for various companies, I didn't see any that are actually approved to the supplemental protector standard. So these things are kind of in a category all their own. Probably the reason they're not being done as supplemental protectors is they don't have an interrupting current rating. The standard 2367 is a complete mystery to me. You go to UL with an ECP product and explain to them what it is, and they will come back and say, okay, yep, 2367 is the standard that applies to, or the only standard specific to ECP, except it doesn't seem to be. Clause 1.3 says the devices covered by these requirements are entirely electronic in nature and no means for manual operation or reset. So an electronic circuit protector that can't be reset would be very much like a fuse, I would think. So I'm not sure how anything in the ECP offering today on the market could possibly meet standard clause 1.3, but that's in the standard. And then there's clause 1.4, which babbles on for a while and then finally ends with intended to be mounted on a printed circuit board. So standard 2367 was written around products called PTCs, positive temperature coefficients. And these were launched, several companies started making these, and they offer them as electronic fusing. So it seems that this standard was written around those, or possibly around MOVs and other protective components. The other real strange thing about that standard is UL will ask that demand that the product be redundant. So that if the main overcurrent protection circuit fails, there's a secondary or backup circuit to interrupt the current. Part of the idea being, well, you know, what if the electronics goes flaky, or what if the MOSFET short circuits and now you don't have any protection anymore? So to get your product to pass 2367, looks like it has to be redundant, and there is absolutely no mention of that in the standard. I thought we did a product at 2367 several years ago, probably 10 years ago, And I figured, oh, well, I'll get the most recent version of the standard and see if they've added this clause explaining the redundancy thing. And it's still not in the standard, but it's still a requirement. So you'll see on some companies' products, they have 2367, and it's an electronic circuit protector, but if you get a schematic of the product, you'll find there is actually a fuse internal. You could do redundant electronic circuits and just fine tune one for 0.5 amp and the other one could trip at 525 milliamps, and there's your redundancy, but it makes it very expensive to put in the double up on the electronics. So if you're certifying your product to 508 or 14, you don't need redundancy. So the products, if you're looking at an EC product and it's done to one of those two standards, it's not exactly the equivalent to a product done to 2367. But if you are using these things on the output of a DC power supply, the power supply provides the redundancy. If the ECP product doesn't interrupt the current, the power supply goes into fault mode and shuts down. So I would argue that if you have a 508 version of an ECP product and it's for DC applications and you're using it with a certified power supply, there's absolutely no need for the redundancy required under 2367. It's my opinion. And why not test these things to the supplemental standard 1077 or CSA 235? That would seem logical, except you have to know what the short circuit current rating is. And it's very hard to determine that for solid state devices. The component itself might have an interrupting rating, but then you have to factor in all the resistances in series with it. And it's very hard to come up with a short circuit current rating for an ECP product. I think the most likely way to determine if it's got a suitable short circuit current rating is to short it to ground and see if it turns off before the power supply does, and then make sure it doesn't burst into flames and it works a second time. So I think that's the block between getting the product rated as a 1077 supplemental protector, is that it doesn't have a short circuit current rating. And here's just, some of the products that are on the market today. There's one out of ETA, German company, ESX10. They launched in North America, I'm not sure, about 10 years ago, maybe 8 years ago. And they launched as electronic circuit breakers. And I believe they were given the cease and desist notice from UL to stop calling them circuit breakers. The Bulletin 1692 product from Rockwell. This one is it's a multi-channel unit. So the cost per channel comes down significantly compared to the, for example, the ESS10, which is a single channel unit. You can see the ESX10 here has an on-off switch in the front. So that's why they were calling it a breaker, because you can manually turn it on and off, but it doesn't meet the definition of breaker according to electrical codes. Muir Electronic has a little 4-channel device. We make one, if we have time, we'll talk about it a little bit later, for 4 to 20 milliamp loops, where if you want to protect the power going out of your panel to the transmitter in the field, you could put this in. It lets 20 milliamps go by, and at about 30, it would clamp and shut off the loop. We did a 16-channel unit. This was a prototype for a project where you can see there's a row of push buttons on there. And then if any one of the 16 channels goes into overcurrent protection, shuts down, in other words, you would reset it by hitting that button. An ECP product, you could design the circuit to latch off. You could have it reset as if it was a thermal supplemental protector. You could reset them by a remote signal. The flexibility, because it's electronic circuit, you have all that flexibility that you wouldn't on a breaker or fuse. You also have the ability to turn them off remotely. So compared to a shunt trip breaker, the shunt mechanism could add considerably to the cost, where an ECP product could just be a digital input from the PLC or from a push button somewhere and you've turned it off. So they have their advantages. Speed is the main one. For DC applications where the power supply is the upstream redundant protection, ECP products make a lot of sense. You can get very accurate trip points. You don't need to worry about how much boost power you can get out of your power supply. But you should test them with the power supply to see that they can handle the fault current. And as mentioned earlier, the non-arcing sparking nature makes these things ideal for class 1 Div 2. And there are a number of these on the market that are certified for hazardous locations. The regulatory issue, that standard 2367 still perplexes me, but you just have to understand it's seemingly there to create the need for this redundancy, as if the product's going to be used on its own, not downstream of a device with current limiting. That was it. I ran through that kind of quick, but are there any questions?
Don, I don't see any questions at this time.
Okay. Oops, that's not the one I'm looking for. Can you guys see that screen? Some new D-Pro products. Did that pop up?
Not yet.
Not yet. All right, let me. Well, where did that go?
Don, while you're setting up, I'm hoping everyone can hear me. This is Mike Masterson. I want to make everyone aware that we've talked about Rock Live, which is the Rockwell trade show that's coming up in, I believe, May 10th, or excuse me, June 10th. I want to make everyone aware that registration for Rock Live and all the labs will open on May 4th. So they will be opening on Monday. I'm glad to let you know you're the first people we've told this to. So just get your calendars ready. We want as much Texas representation at Rock Live as possible. So there's going to be over 18 online labs being done. Hopefully by tomorrow, you might want to check with your sales reps or your automation specialists, and we actually might have a list of the classes and trainings going on. But registration for Rock Live will open on May 4th. All right, thank you.
Did I get it right yet? Can you guys see that screen?
Yeah, you're good.
All right. Oh, sorry about that. Just show you a couple products that we have for overcurrent protection. This is the one I touched on earlier for 4 to 20 milliamp loops. It would sit between the power supply and the field wiring going out to the transmitter. So this would take 24 volts from the power supply through this device, runs the transmitter, the analog signal goes back to the PLC. If you get a short circuit in that wiring, this device will clamp the current at 30 milliamps. So the power supply will never get a chance to switch off. Its overcurrent protection isn't going to kick in until 5, 10, 15, 20 amps, depending on the size of the power supply. This one is going to limit at 30. The loop would go dead, so the PLC would lose the analog signal. And it has a make before break jack sitting here in the middle. So that's where you could plug in. We have a little cable that would go between your meter, plug into this device. You could take a current reading during commissioning or troubleshooting or calibrating. And when you want to move on to the next circuit, you just unplug and move on. There's no sliding links or disconnects to be operated. For safe area, it's CUL US listed, and for Class 1 Division 2 applications, it's CCSA US. We're going to start promoting a series of circuit breakers soon. These are currently ATEX, IEC, EX rated. They're 1 to 60, somewhere between 1 to 63 amps. You can get 1, 2, and 3 poles with auxiliary contacts. Currently direct mounted. We may offer a DIN rail mounting adapter. They're pretty heavy, so I'm not sure DIN rail mounting is a great option. And as soon as the COVID nonsense is over and we get back to UL, we will start the process for getting UL 489 and dealing with CSA for either Class 1 Div 1 or Class 1 Div 2. And another one, this just got approved recently, and we're going to build the initial inventory shortly. This is an 8-channel supplemental protector for 24 volt. There are 120 volt versions as well, but I think it's going to be most popular for 24, where you get 8 breakers, supplemental breakers here with a little reset button. You get 2 terminals per channel, the line and the neutral, or the 0 volt and the 24 volt. So it's kind of the equivalent of 8 supplemental breakers plus 8 terminals for the neutral and a bunch of jumpers. It has an option here. You can see we can plug in a little cable over to an adjacent module. That's a monitoring module, monitors the status of the 8 breakers. If any one of them trips, this thing changes state, sends a signal to the PLC or to an alarm or indicator on the door of the panel or something telling you that one of the breakers has tripped inside. All Class 1 Div 2 certified. This just shows that to access the breakers, to reset them, there's a hinge cover here on the front, and you pop that, you loosen 2 screws, open the cover, and you can reset your breaker, put the cover down, tighten the screws again. And the whole cover and screws thing is to the CSA UL requirements is they want to slow you down so you can't just reset the breaker without checking to make sure the area is safe and there's no explosive gas. So there's warnings on the front. Then you loosen the screws, open it up, reset your breaker when you know it's safe, and close it up again. So this is this unit's going into production shortly, and we'll be sending out the literature and the release documents hopefully in May. And that was it. Yeah, that was just a couple of the products that we'll be coming out with shortly. Any questions, or we okay?
Doesn't look like we have any questions, Don. We do appreciate you leading us on this seminar, and thank you for your time.
All right. Thanks very much, everyone.